Thanks a lot, Analytics Vidhya, for giving me this opportunity to share my knowledge with the larger crowd. Before we move on, I'll just give a brief introduction about myself. Hi, I'm Rituparna, and currently I'm working with the Microsoft Cloud Data Sciences team. And like in Microsoft, I'm working in a lot of interesting use cases, starting with generative models, reinforcement learning, and with a lot of machine learning engineering. So this session, like before I start, I want to give a heads up to all of you that, like in this session, like along with the machine learning aspect of things, I also want to like focus on the ML engineering aspect of things, how to package the models, how to deploy the models, because what usually happens is that we as data scientists, we get so busy with the building up of the models, we tend to ignore all these aspects of like modeling, which are actually very important. How to package a model, how to kind of deploy a model. So many times I've seen that beautiful state of the art models being just built out in Jupyter notebooks, and that notebook is being shared across everyone. So when you're working in a product based setting, that is not actually the best practice, to be honest, because once when you share your code with someone, you have to give them the right KT, and giving KT to a lot of people is very time consuming. So along with the machine learning part of things, I also want to focus on the operations part of things also. So this will be the highlight of today's session. So let me share my screen, just give me a minute. So the topic of today's session is building an end-to-end machine learning pipeline for large language models. So when I say end-to-end, it will not only like involve, kind of fine tuning and building the machine learning models, but also building an end-to-end pipeline in which, we can deploy and publish the models. So before I move on to that part, we have been, there has been a lot of buzz around LLMs, large language models. Like every company is trying to come up with its own version of large language models, and there has been such a fierce competition among big techs like Microsoft, Google, Facebook to come up with their own versions of large language models. So what exactly are these large language models? So large language models are deep learning based models which process natural language based input data and generate responses in human language, in human like language. So I'm pretty sure like a lot of you would have by now tried, chat GPT, and you would have seen that, if you ask the chat GPT, say, write a story on this particular topic, or write a like paragraph about this particular topic, so it instantly gives you a human like a human like so something which has written by something which has been written by a person actually. So its output is something very similar to what has been written by a person, so it's very much human like. So like this is what exactly a large language model does. Interprets it interprets an input, a prompt, which is a natural language based prompt, and generate responses which are human like, and which can be interpreted by us in a normal manner. So like we have been hearing a lot of large language models, and some of the common ones are like the GPT, which is which has been created by OpenAI. Then we have BERT, which has been created by Google. Then we have Roberta and Llama, which has been created by Facebook. So these are some of the most prominent large language models, and some of the names which we are commonly hearing these days. And along with that, Google has come up with its own version of large language model, which is called BART. So these are some of the very commonly, these are some of the very common terminologies which we have been hearing now and then. So like, why are they exactly called large language models? Because these language models have been trained on a huge corpus of data, and these models essentially contain like billions of parameters. For example, GPT 3.5 contains 175 billion parameters. So because of the fact that they have been trained on a huge corpus of data and they have billions of parameters, so that is why like they have derived this name large language models. So why are large language models so much trending these days? So one of the reason is that the large language models have achieved state of art performance on a wide range of natural language processing tasks, like language modeling, text classification, machine translation, question answering, then summarization. They have just like raised the benchmark of all of these processes. So a lot of you would have tried coming up so a lot of you would have tried out chat gpt, and you would have already like experienced the different tasks which chat gpt is doing, like summarization or say question answering, and you would have seen that it performs extremely well on these tasks. So because these models have state of the art performances, that's why the big techs are so much crazy about these large language models. Now coming to next, these models, because these models have been trained on such a huge corpus of data, it makes them excellent for few shot and zero shot learnings. So what is few shot learning? So few shot learning are those are those instances where you have very less number of instances for a particular class, and zero shot learnings are those where you have almost no instances of a particular class. Say for example, an unsupervised learning. So large language models perform extremely well on few shot and zero shot learning tasks. So large language models are trained on a vast amount of data, which makes them very efficient at using the data. By pre-training on large amounts of data, the models can capture a wide range of linguistic patterns and relationships, and that's why they perform very well on the downstream tasks with with minimal additional training. So that is why they have been so much trending these days. Then the next and the most important thing, which I believe all of us have experienced, is automation. So large language models can automate many natural language processing tasks that were previously done manually. Say you can ask chat gpt to write a speech impersonating a particular movie character. So large language models have caused a lot of automation when it comes to content generation. Large language models can also generate codes like very efficiently. They can generate very complex codes of sql, python, with a lot of efficiency. And also, like large language models have been projected to be used for automated eda on data sets, which we shall be discussing today. So like as the efficiency of the large language models is increasing, the need to have an automated EDA on datasets is also increasing. So that's what we are going to discuss today. So just a brief overview on the architecture of large language models. So most of the large language models are based on transformer architecture. So they share a lot of components of the transformer architecture, like the encoder, decoder, the self-attention, the multi-headed attention, which is a variation of self-attention. So these are the underlying building blocks of most of the large language models are transformers. So I'll give one illustrative example of GPT. So GPT is basically a variant of transformer architecture. So a GPT consists of a stacked transformer. So GPT consists of a stack of like transformer encoder blocks. So it consists of a lot of like stacks of transformer encoder blocks, and each of the transformer blocks contains two sublayers. Okay, so one is a multi-head self-attention layer, and one is a position-wise feed-forward network. So if you would see this particular diagram of the GPT architecture, so if you can see over here, so it contains a stack of multiple transformer blocks. So this layer 1 up till layer I, these are stacked transformers, and and this is basically a positional encoding based architecture, which we shall be discussing next. What's his utility is. So so in the self attention layer, which is inside the transformer block, the model computes a weighted sum of the input token embeddings, but the weights are determined by the dot product between each token's embedding and the embeddings of all other tokens in the sequence. So basically what it does is that it tries to give relative importance to each component of a sequence. So it might happen that some components of a sequence might be more important than the others, so it helps to bring out the important ones and mask the unimportant ones. So this helps to bring a sort of relevance to the sequences. Now this is basically the self attention layer. Now there is also a position wise feed forward network. So this one which you are seeing over here, the positional encoding, this is actually the position wise feed forward network, which applies a non-linear transformation to each token's hidden representation. So this nonlinear transformation is actually responsible for the for the state of art performance of the GPT model. So whatever performance you are seeing of the GPT model, it's because of this non-linear transformation which is applied to each token, and this helps the model to capture complex relationships between the tokens and learn more about the abstract representations. So this is why the GPT models perform so well. In addition to the transformer blocks, the GPT architecture also includes an embedding layer which maps each input token to a fixed size vector representation, and a final output layer which computes a probability distribution over the vocabulary of possible output tokens. So this softmax layer which you are seeing over here, this is the final layer which computes a probability distribution over the vocabulary of possible output tokens. So this is in details how the GPT architecture works. So the models which are hearing about, like GPT 3.5, they are an advanced version of normal GPT, and GPT 3.5 has other additional features to it, like meta learning, prompt based learning. So these are some of the additional features you will find in these kind of models like GPT 3.5 and all. So LLMs for automated EDA. So this might sound a little strange, but LLMs these days have been projected to be used for automated EDAs from data sets. So you give it a data set and you put a query in natural language, and it's going to fetch you the required result from the data set. It is similar to writing a code in Python and SQL and fetching the relevant results. So some of the architectures which have been proposed for automated EDA are TAPEX, which has been designed by Microsoft, TAPIS, which has been designed by Google, and Table QA. So Table QA is one of the advanced version amongst all these three. So Table QA can can generate EDAs, can generate SQL codes out of the data, and can also generate charts also from the data. So table Q&A is actually the most advanced one out of all these three, which uses a BERT question answering based backend. So today we will be discussing TAPEX based automated EDA. So TAPEX uses a BART architecture in the background. So So what is the BART architecture actually? Like I will explain it to you towards the end, once when we complete with the code demo. So in the interest of time, I have kept this part towards the end, and we can discuss this once we have done the code walkthrough. So, so coming on to next, I'll tell you a bit about Azure ML Studio. So this is exactly what an Azure Machine Learning Studio looks like. So most of the work which we do in Microsoft is, based out in Azure Machine Learning Studio. So like what usually happens is that, many times, we as data scientists, we end up building the work in our locals and in Jupyter notebooks, and we often forget about this aspect of work, where it involves packaging the model, publishing the model, making the model available to stakeholders, especially who are non-technical. So say I have a model which is like written out in Jupyter notebook, and I hand over that Jupyter notebook to a stakeholder who doesn't have a lot of knowledge about machine learning. So it becomes very cumbersome for me and for the stakeholder also, because the stakeholder is going to face the steep learning curve, which comes with, the code deep dive and all. And for me, I'll have the additional burden of giving the KT to the stakeholder. So with that thing in mind, like in Microsoft, we use the Azure Machine Learning Studio, which is a shared workspace where most of our work, notebooks, codes are are kept in a collaborative manner. So it's here actually, where we have all our code bases, data and everything. And it's here where we deploy our model, where we register our model. So this is actually the most commonly used thing across all the Microsoft. So starting with the Azure Machine Learning Studio, the very first thing which you have in an Azure Machine Learning Studio is a workspace. Okay, so this is how a typical workspace looks like. So this is the default directory. This is the home page of Azure Machine Learning Studio, and this is how a typical workspace looks like. To create your own workspace, you need to have an Azure subscription in place, and using that you can create a workspace for yourself. So I have a workspace for me, which is called My Workspace, and this is how it looks. It has all my notebooks, all my code and everything. So what exactly is a workspace? So workspace are, places where we collaborate with our colleagues to create machine learning artifact and group related work. So we create experiments, jobs, data sets, models, inference endpoints. Okay, so the basic functions of the basic utilities of a workspace is, once we create a workspace, we can manage our data using data stores. So guys, there will be a lot of jargons, you will come across. I would request you not to get overwhelmed, because down the line I'll be explaining, all those jargons, like, data stores, inference endpoints, experiments. So down the as we go ahead, it will be more clear to you. So once we have a workspace in place, we can manage our own data, we can run experiments. So experiments are nothing but, triggering a machine learning pipeline. So I have a model and I can trigger the pipeline to kind of run the model or train the model and get the result. So this is one thing. And in a workplace, we can manage our models, we can track, we can monitor, we can track our experiments, our models. So a workspace is basically a collaborative environment. And the best thing about workspace is that, you can view the code which your peers have written. So this leads to more collaboration amongst the groups. So besides all this, the workspace also has a lot of resource configuration, like, compute targets. So compute targets are used to run machine learning experiments. Then data stores. So data stores are nothing but they are used to store the data in a workplace. And then security setting like networking, identity, access control, encryption settings. So I'll be explaining to you how to build a pipeline for a machine learning model. So before that, let me explain you the model which I have with me. So today I shall be explaining to you the Tapex model by Microsoft. Okay, so Tapex is nothing but it's a model for automated EDA. So I'm using this transformers library from Hugging Face to kind of use the Tapex model. It's also available in Hugging Face also. So say I have this kind of data. I have a cancer data which looks something like this, that year, nationality, gender, where the cancer has occurred, what's the death count for that particular year, nationality, gender combination, and what's the age. So this is how a Tapex model looks. There are two parts to it, Tapex tokenizer and BART for conditional generation. So BART, as I had mentioned to you, is another large language model which forms the backend of Tapex. So I download both of these. So here I've sliced the data just to some 20 records, just for the sake of computational for computational reasons. And I have this data. This data is passed on to the tokenizer, and then I pass it, and then I pass a query to it. How many death counts are due to esophagus cancer? So as you can see, it generates a result like this. So so there has been one death in the entire data due to esophagus cancer. Now when I do when I do its respective pandas operation, you could see that there has been one death due to esophagus cancer. So it's able to accurately predict the number of deaths due to esophagus cancer given natural language input. So instead of doing a lot of pandas operation, I've just given in a natural language input, and it has given me the result. So this is the model which we will be dealing with. And to kind of construct any pipeline and to kind of construct any pipeline, any service within Azure ML Studio, we need this Azure ML.core library. So this contains core packages, modules, and classes for Azure machine learning. So this is the most important library which we shall be seeing. And apart from that, we will be constructing a pipeline using the pipeline library. So Azure machine learning pipelines, they allow us to create reusable machine learning workflows that can be used as a template for machine learning scenarios. So this is how a machine learning pipeline looks. I'll just show you. So this is exactly how pipeline looks. Okay, so you have a pipeline endpoint, and within each endpoint you have multiple pipelines. So this is how a pipeline looks like. So if you trigger this pipeline, it triggers a machine learning models. It triggers a machine learning model, and in this way, it triggers a machine learning model and does its assigned task. So this is how pipeline looks like. A pipeline is nothing but a workflow for a machine learning model. So understand pipeline this way. It's a workflow for a machine learning model inside the Azure ML Studio workspace. And then apart from and then once we create a pipeline, there should be something the pipeline should trigger. So what exactly should a pipeline trigger? It can be a model, it can be a Python script also. So we have built a pipeline, like the pipeline triggers a Python script, and this script gets passed in the Python using the Python script library. So there is this Python script step library, like where we pass in the Python script, which gets triggered by this pipeline. So so as you can see, here we have the pipeline library, and here we have the Python script step library. So here, we are assigning the workspace. So we are extracting the configuration of the workspace. So this is how the configuration of the workspace looks like. So this is the name, the resource group. This is the location. So so this is how, so this is a workspace basically. As I told you, here we are extracting the configuration of the workspace. So we have so every workspace has a name. Then there is a resource group of the workspace, then a workspace location. So this location is actually, where the workspace server is located. So for me, the server is in East US 2, and a subscription ID. So this subscription ID is what you require, to access any cloud-based service in Microsoft. So this is a paid subscription ID, but I think you get it free for some time, probably for the first 3 months apparently, or I'm not sure about it. But this is a paid subscription service, which you need to take to access any cloud-based resource in Microsoft. So this is a workspace. Within each workspace, we have something called data stores. Okay, so data stores are nothing but, so as the name suggests, they are Azure storage services, which are used to store the data. So this is how a data store typically looks. So every workspace has different data stores. So workspace, working directory, workspace, blob, which is the default blob storage, and which is the most widely used storage, the storage capacity which we use. Then workspace artifact store, workspace file store. So this is essentially, what is a data store. And there are different Azure storage services which can be registered as data store. So some of them are like Azure Blob Container, Azure File Share, Azure Data Lake, Azure SQL Database, Databricks File System, Azure Database for MySQL. The most commonly used Azure storage is Azure Blob Container. So this data store which you saw, this workspace blob store, this is actually the default blob storage container which is associated with our workspace. It's used to store various artifacts and data associated with our workspace, like CSV files, then Excel files, scripts, .py files, IPyNB environment files. So this storage service is essentially used to store all these information. So when we are creating a workspace in Azure machine learning, the workspace blob storage container is automatically created for us, and we can access this using the Azure machine learning portal. So a small example of how you kind of load a data into the Azure blob storage. So I have a data stored in a particular location. I use HTTP protocols to kind of fetch that data. And here as you can see, def blob store dot upload files, this is what uploads the file into the blob storage, and then upload call complete. So this is how we upload our data to the blob storage. But for this particular demo, for the sake of complexity, I've not, and because of the limited time we are having, I have just used up pd dot read CSV function to fetch the data. Now coming to the most important part of Azure machine learning service. So in Azure machine learning studio, we have something called compute instances, which are cloud-based workstations for data scientists. And every compute instance has only one owner. So what exactly are compute instance? These are actually the X factors which come up with your Azure, which come up with your cloud platform. So this is how a compute instance looks like. We have two types of compute instances. One is a CPU based compute instance and one is a GPU based compute instance. So CPU based compute instances are used for lightweight, data analysis, data crunching and all. And GPU based compute instances are used for, heavyweight training, like, training heavyweight deep learning models, training, testing, fine tuning deep learning models. So this is why, we prefer using the Azure ML Studio rather than our local system, because it comes up with a lot of GPU options. You have 12 cores GPU, you have 16 cores GPU, you have 24 cores GPU. So there are a plethora of GPU options which you can choose depending on your task. So the most commonly used GPU are, NC12 machines, and sometimes when we are training heavyweight models like reinforcement learning based models, we use the NC24 GPUs. So this is actually the X factor which comes up with, the cloud platforms. So this is what is a compute instance. So moving on to next, we have a compute instance, and then there is a compute cluster. Okay, so compute cluster is a group of virtual machines that we can use to distribute and parallelize our machine learning workloads. So basically so we have a compute instance, and then we have compute clusters, which are the larger subset of compute instances. So within each compute cluster, you have compute instances and also virtual machines, which helps you to parallelize your machine learning workloads. So it helps you to scale your machine learning workloads to multiple nodes, and enabling you to train larger models, process more data, and gain more speed. So when we create a compute cluster in Azure Machine Learning, we choose the size and configuration of the virtual machines that will be used to run the cluster. So this is how a compute cluster looks like. So here you have compute instances. Here you have compute cluster. So this is a GPU based compute cluster which has one node. So I have created a single node GPU based compute cluster for my task. So I'll just show you. Within this, it looks like this. So whenever you have a process running over here, you will have it in blue. So it will say that a process is running. So this is how a compute cluster looks like. So compute instance has only a single node. A compute cluster can have multiple nodes, but for our use case, I have so I have created a compute cluster with a single node. So this is how you create a compute cluster. So here you give the size of the VM. I've given a standard NV6, a GPU based VM, and minimum number of nodes is 1, maximum is 4. So this creates a compute cluster for me. And once the compute cluster is created, this prints a message like this, that Azure machine learning compute attached. So moving on to next. we have something called a run configuration class, so this so whatever we have seen above, the compute cluster, the compute instance, this run configuration class is used to wire all of these together. So this is a class to set configuration setting for Azure machine learning experiment. It allows us to specify settings like compute target, environment, script parameters, and everything. Okay, so here we have the run configuration class, and here we have something called a default GPU image. I shall be explaining to you what's a default GPU image. So default GPU image constant is a predefined value in Azure machine learning that represents the default Docker image for GPU enabled compute targets. So it's a default Docker image for GPU enabled targets. Such image includes common deep learning libraries and frameworks such as TensorFlow, PyTorch, Keras, as well as CUDA, CUDNN. So these libraries are all there with it, for GPU acceleration. So when we are publishing our pipeline, all these GPU frameworks are all wound together with our pipeline. So that's why we use a predefined default GPU image. So here you have the configuration class. It's initialized. Then then we set Docker enabled is equal to true. We are enabling the Docker, and we are assigning the Docker base image over here. So over here we specify the we initialize the run config variable, and assign the default Docker image. Now, once we have our pipeline ready, how are we going to install our Conda dependencies or pip dependencies into the environment? So for that, this Conda dependencies class is used to specify what packages and what versions do we want to we want to install in our in our compute target. So which we are having. So here we can add in whatever pip packages we want, whatever Conda packages we want. We can also specify the version of the Python if we want to. So this is how we do it. So you see over here, run config environment, Conda dependencies is equal to. So here we pass in the Conda packages. So for Conda we have scikit-learn, and here we have the pip packages like pandas, Azure ML Core, PyTorch Lightning, then and then you have transformers, and you have torch. So this torch is actually the library for PyTorch. And we assign our compute instance to the run config target. So after all these things are done, so we have something called a Python script step. Okay, so everything, this pipeline at the end triggers a script. Okay, so in here we have this entry.py script. So so this is basically how my script looks like. So I have I have two arguments in here. One is the data, and one is the question. What I want to ask to my data. So this is actually the script which I shall be triggering. This contains nothing but the code of Microsoft Tapix, which I had showed you earlier. So so as we saw, that particular Python script requires some arguments in place. How are we going to pass those arguments into the Python script? So for that, we have the pipeline parameter library. So over here, we define the pipeline parameters. So the name of this parameters is data, and the default value is none. Similarly, the name of this parameter is QUES. quest, and the default value is none. And next, what we are going to do, we are going to pass these pipeline parameters in the arguments, in the arguments parameter over here. So we have the Python script, we have what arguments we want to pass to the Python script, and we specify other arguments, like what's the target in the run config, and what's the run config. So these informations we pass in, and this completes our Python script step. Okay. Now next, we have everything in place. We initialize the pipeline. So this is how we initialize the pipeline. We give in the workspace, and we give in the steps, So this pipeline has got just one step, which is this step. So it can have multiple steps also. So it can have a Gen 1, Gen 2, Gen 3. It can have multiple steps also, which run parallelly to each other, or which can be linked to each other also. In our use case, we have just one step over here. And this is how we initialize and create a pipeline. Now after we create a pipeline, what happens is that so we create this pipeline, like what's the entire motive of creating a pipeline? To make our model to improve the encapsulation of our models. Okay, now once my pipeline is created, how am I going to access that particular pipeline? So to access that particular pipeline, we need to make it available as a REST endpoint, which can then be triggered through HTTP requests like GET, POST, and all. Okay, so the best thing about this is, now if you have made a model, you want to share the model with someone, so you don't have to just share your entire Jupyter notebook and all with the person. All you need to do is share the URL of the REST endpoint, and what all parameters you pass into that URL. That's it. And then the person can trigger your pipeline. He can train a new pipeline. He can inference from the existing pipeline. That's it. You need not share your entire code base with a person. This is especially useful in cases when you are dealing with non-technical stakeholders, which happens a lot when you are working in a product-based setting or in a consulting-based setting specifically. You work with a lot of non-technical stakeholders, and these kind of approaches are very essential, to kind of encapsulate your model properly, and also helps in smooth handing over of your results to the stakeholders. And to publish a pipeline as a REST endpoint, we use a pipeline.publish function. So this kind of publishes the pipeline as a REST endpoint. Okay. So you have published your pipeline as a REST endpoint. So so that is done. Now now suppose after some time you want to make some changes to your pipeline. Okay, and you made some changes to your pipeline, and you republished it. So in that case, what's going to happen is the published URL is going to change. Okay, now if the URL is going to change, the URL which you have given out to somebody else becomes obsolete. Okay, so this poses a lot of problem, because once you create a pipeline, you shall be making a lot of changes to the pipeline, for sure. Okay, like once we have models, there is a lot of to and fro in the models. Okay, so what you can do in this case is, so what will happen in this case? First, you can use this pipeline endpoint library to detect if there is an existing pipeline available. Okay, so if there is an existing pipeline available, so if an existing pipeline is available, it will just append the published pipeline to that endpoint. Okay, so you may not have to create a separate endpoint altogether. So what it's gonna do, it's just going to append this published pipeline to the already existing endpoint. Otherwise, if there is no endpoint in place, it is going to create a fresh endpoint. It's going to kind of publish a fresh endpoint in here. So this is like how it looks typically. So if you would see over here, so this is the endpoint which I've created. This is the endpoint which I have created. Okay. So over here, like I can make n number of changes to my pipeline. Okay. But this REST endpoint URL is going to remain the same. Okay. The only difference which is going to happen is in this published pipeline, my new pipeline is going to be added and will be marked as a default pipeline. So as you can see over here, there are multiple pipelines over here, and this is my default pipeline. Okay. So in this way, what's going to happen, I can make n number of changes to my model, and at the same time, the REST endpoint URL, which I've shared with the stakeholders, does not become obsolete. So this is typically how a pipeline endpoint URL looks like. So you have done everything now. You have published the pipeline. You have you have set the compute cluster, the compute target, and everything. Now, how are you going to access your model? So the very first step for accessing a model is using the Azure CLI based authentication. Okay, so this Azure CLI class helps to authenticate Azure ML workspace. It helps to authenticate the Azure CLI using your existing Azure ML workspace credentials. Okay, so you won't have to repeatedly authenticate yourself by passing in your password, by passing in your username repeatedly. So this kind of smoothens the process of automation for you. And then you have something called AAD token. Okay, so AAD token is nothing but a security token. You know, it's used for identification in case of AAD protected resources. You know, so when you have a protected resource is something which is inside a workspace. Okay, and when you are trying to access a protected resource, you need this AAD token. Okay. So this token contains, you know, information about the identity of the user or the application, and this is how it kind of tries to authenticate. So I have this request library which is in here, and I'll be using again the cancer dataset which is there. And this is how the data looks. As I mentioned before, year, nationality, gender, like the site in which the cancer has happened, the death count, and the age. So I'm going to demonstrate exactly the same thing which I had showed you before for the latex demo. So I create a JSON payload. I have these parameters. I create a JSON payload. This is my REST endpoint URL. This is my AAD token, and I'm triggering the pipeline. Okay. So this is how a response variable looks. So if I go back to my workspace, I will have a machine learning job created over here. So this is the job which I've run right now. You can alternatively also access the job this way. So once when you JSON dump this response thing, so what you can do, you can open this, and over here also you have this URL of the run which is there. So what you can do, you can just copy paste the URL in your window. So this way also you will see, you know, like if your experiment has run. So there's also one way to kind of view your experiment. Okay. So once my experiment is done, I will kind of check the results. So over here, I will have the results. So once when you have the experiment done, you will have this kind of box in here, which gives the name of the script which has been executed. And once when you double click on that, you will see the entire log of the run, and like whatever log of the results which you have. So like whatever log of the results is there, I'm storing it in the matrix part. Okay. So how many total number of deaths occurred due to oesophagus cancer? The answer is 1. So it's able to like perfectly kind of extract the information using a natural language query. Okay. Now let us try to give it some more complex queries. So as you can see over here, like oesophagus cancer, like this is one person with oesophagus cancer. Okay. I give it a second query. Okay. Which type of cancer has the maximum death count? I triggered this. So over here, essentially, breast cancer has the maximum death count. Let's see if like it's able to predict it or not. Has the maximum death count. Now I have sampled the data into some 20 rows, and this is my file which is there. So this is essentially how my data looks like. It's just a subset of the data which you are seeing, because this particular model, it has limitations of data and all. It can't handle like a large volume of data. So which type of cancer has the highest death count in the male population? Okay. I triggered this experiment. So for so for male folks, colon cancer has the highest death rate. Okay, and let us see if our model is able to predict this or not. And the model is able to perfectly predict that like colon cancer has the highest death rate in the male population. Now moving on to some more examples. If I ask the model, which are the different types of cancer present in the female population. So essentially the female population has these type of cancer: brain, bronchus and lung, gallbladder, leukemia, liver, and intrahepatic bile duct, ovary, skin. So let us see like what the model is able to predict. And the model is able to bring out all these, though it's not able to capture everything, but it's able to capture 90% of the data. So brain, nervous system, skin, leukemia, ovary, bronchus and lung, gallbladder. Only liver and intrahepatic only liver and intrahepatic has been left out. So next, I give it a I give it a query something like this. Which cancer has the highest death count for the expatriate? So expatriate, if you would see the data, is a type of nationality. So which cancer has the highest death count for expatriate? So for expatriate nationality, brain cancer has the highest death rate. So let's see if it's able to. So brain cancer has the, so it's able to predict accurately that brain cancer has the highest total death count for expatriate nationality. Now one thing, if you would see over here, so for expatriate nationality, there are actually multiple other cancers, which have a high death rate, like leukemia, then ovary and all. But it has detected just one of it. So you can consider it like a limitation of the model. So it's able to detect one of it, but not all of it. So this is kind of a limitation which comes up with the model. So this is this one now. Which cancers have the highest total death count for national females? So national females, meaning females which have females whose nationality is national, who are not expatriate. So essentially, for those females, like females who are national, so for them the two highest the cancers with the highest death rate are breast cancer and liver and intrahepatic cancer. So let's see if it's able to predict it or not. And there you go. So as you see, it's able to perfectly predict both of it. Like as you can see, liver and intrahepatic bile ducts and breast cancer. So these are the two cancers which have the highest death rate amongst female nationals. Now, the last query: which cancer has the highest total death count for expatriate males? So if you would see expatriate males, colon cancer has the highest death rate. So let's see if it's able to capture this information or not. And there you go. It has perfectly captured that, colon cancer, the cancer with the highest death rate amongst expatriate males is colon cancer. So as we saw that, this model is able to perform at least the basic EDAs, properly. Though the model has, its own set of limitations when it comes to like joins, merge, and all, it might not perform properly when it comes to complex queries. But at least basic EDA queries, it's able to perform with a good accuracy. And given that, as the quality of the large language models is will increase, as their performance will increase, these tasks will also have a so the accuracy of these tasks is also going to improve, going ahead. And with the advent of large language models, there is a lot of scope for automation of the EDAs. So this is where I conclude. And anyone who has any questions, you are free to come up. Am I audible to everyone? So I see over here so I see over here there are few questions that her reinforcement learning is also involved in chat GPT based architecture along with the transformer based model. If yes, then how? So of course reinforcement learning has also been implemented with the chat GPT architecture. So along with your transformer architecture, they are using a reward based mechanism. So if you would have noticed the chat GPT page, there is a thumbs up and there's a thumbs up and there is a thumbs down. So using that, you can provide your feedback that if the answer which has been given to you is correct or not. So in this way the feedback gets passed on to the model, and there's a reward based mechanism which is which further fine tunes the transformer based architecture. So is reinforcement learning there in the chat GPT architecture? So the answer is yes. It does have a reward based mechanism underneath it. The next question, what is the max data size we can pass in params to pass it to the model? So if I understand, max data size, you mean what is the max data size we can pass to the TAPEX model? So actually there is no rule of thumb to how much the data size is, but like once you have some 100 records, the Tapex model starts like showing some problems. So both, it's not just with Tapex but also with Tapas, which is like a model by Google. Both of them have data limitations as of now. For Tapas, it's I guess the batch size should be 512. For Tapex, I've seen that once when it goes above 100, some problems start to come up. That like out of memory and all. So both these models are like having like these issues definitely. So and the next thing is that in case of overfitting, uh, how can we like handle those features? So when you are talking about large language models, actually large language models, these models like Tapex and like Tapas, like they have been like trained over like a very large corpus of data. Okay, so what happens is actually that when you have when you have a model trained over such a large corpus of data, the generalization power of the model increases actually. So this kind of like like leads to less of overfitting. Okay, so so to avoid overfitting in these kind of models, like Tapas or Tapix, to try to use like some sizable data, which you have, and then like apparently you will have a larger corpus for the model to learn from. So in this way you can like address overfitting. So this answers this question. Does Tapex model handle data cleaning if the data set has a lot of missing values? So Tapex model does not handle data cleaning. So actually you have to clean the data by yourself, like before passing it to the Tapex model. If it has missing values, you have to do the right kind of imputation. You have to if there are nan values, you have to impute those nan values. So like Tapex model actually like does not handle the data cleaning. So you have to impute the missing values by yourself. So that answers all the questions. Any more questions by any of you? So like anybody else who has any questions, you can apparently like unmute and ask it. So like I guess we are done with the question and answers. So in case you guys have have any other questions related to large language models or automated EDA, or any of you want to just catch up over LinkedIn, or just have a chat about like what's the like working culture in Microsoft, like how like generic questions about Microsoft or generic questions about my work, you can feel free to reach out to me over LinkedIn. So my LinkedIn profile link has been provided in the DataHour page. So feel free to send me a connection, and I'll try to reach out to you. Bye everyone.